Hello and welcome to my presentation about the year 2038 problem. My name is Arndt Bergman. I've been working on this with a couple of other folks for the past 5 years, and I'm going to give you an update where we are. So who of you hasn't heard about what the problem is about in detail? So I can give you some more background. You all know what it's about, so I'm skip over this briefly. So as you all know, time T is the type that we have in Unix and in Linux, and if it's 32-bit wide, it will overflow. And the fix that we're implementing basically everywhere is to make it 64-bit wide, so it will not overflow until the end of the universe. Why do we still care about this? That's the big question, because a lot of people think, well, who cares about 32-bit anymore? We're all making 32-bit hardware. Everybody's running 64-bit kernels on 64-bit hardware these days. That's all that people make. But if you look at what we're currently maintaining, like we have 5 times as many platforms that are 32-bit in the kernel that are currently maintained, and even the new platforms that we're merging into the kernel. As an ARM SoC maintainer, I see that the number of new 32-bit platforms that we're merging into the kernel is twice as high as the number of 64-bit kernels every single release, and it's been like that for a number of years. I don't expect that to change anytime soon. So we're still adding many new 32-bit hardware platforms. And then, of course, you might ask, are those actually going to be around 20 years from now? Because a lot of hardware is not going to be around. Most hardware has a lifetime of 2, 3, 4 years before it's discarded. But there are certain things, like the Lego Mindstorms are, I don't know, I think this model is something like 10 years old. Kids will be playing with the same thing in 20 years. Because I have the Legos that my kids have are 30 years old, they're still playing with it, why shouldn't they? Another platform that we have in the kernel, the Liebherr industrial machines, cranes and all those have an incredibly long life. And those are running 32-bit kernels. And cars. We get an increasing number of cars running Linux somewhere, and people keep driving them if they don't break. A lot of people get rid of their cars after 5 years. Some people like to drive their same car for 20 years or 30 years. And then some things last even longer, and you might have some 18-bit machines in 2038. So what happens when you're building a deeply embedded industrial machine? By the time something gets into customers' hands, when you buy a $20 million wind turbine, it might already be running a 10-year-old kernel. And that's not because people were doing anything wrong, because they didn't know better. It's just that it takes a long time to get things into production, and then you don't change them as much. And then you expect them to run for 20 years. So in a certain sense, there are already a lot of things in the field that we will have to deal with over the next 20 years that people are not planning to fix immediately. And the sooner we can fix it, the fewer problems there will be. Another completely different area of problems is 32-bit user space running on modern machines. That could be legacy applications where someone lost the source code, the application is still doing mission-critical work. It could be that you have a CPU with 64 bits and you don't have a lot of memory, so you try to make it as small as possible, and running 32-bit code helps. But then if you're running 32-bit user space, you have exactly the same problems to deal with that we have on 32-bit whole systems with 32-bit kernels and 32-bit user space. And there are some distros that just don't exist in 64-bit. So for PA RISC, for example, everybody uses 32-bit user space. Other architectures have gone away from that. Raspbian still uses that. And then one more thing is interfaces that are not depending on the CPU word size. So we have PCI devices that have a register, 32-bit register, to store a timestamp into. When you boot up, start the driver, you put a timestamp into the driver, and then it records events in some internal storage with that timestamp, and it will overflow if it's 32-bit wide. And we still keep adding new drivers like this. So I have this example of a PTP network driver that was recently added. So we're now calling functions to get 64-bit timestamps, and we just truncate them to 32-bit. In a lot of cases, we're lucky in those that we can treat the numbers as unsigned integers. Unsigned integers, if you store a number of seconds in them in 32-bit, rather than having 68 years from the 0 time, you have 136 years. So those are good until the year 2106, unless someone has a bug in there. And that's true for a lot of these things. So real-time clocks, we found tons of different ones, different interfaces, different ways of storing the time, but a lot of them will overflow in 2106. And then file systems is a very important thing. So for example, ext3 or XFS still do not have timestamps wider than 32-bit, and they are explicitly signed intentionally. So they will overflow in 2038, and we will not be able to make them unsigned. So in case of XFS, the solution is we have to add additional fields to store more bits per timestamp. And in case of ext3, the answer is to move to ext4, which has fixed this. But since we have 2 copies of that of the source code, only the newer one implemented the new feature. And then we have user space file formats, and they're everywhere. So these are just 2 examples that I come across. This CPIO, which we happen to use for init RAMFS in the kernel, but it's also used for RPM, for instance, in Red Hat-based distros. And we have the UTMP file format that is used by glibc to store information about who's logged in. And those use 32-bit timestamps. And I'm sure there will be others that we find as soon as we get there in user space and look at all the problems there. So far, my work has been on the kernel. So when did we start? I actually looked at this a number of years ago. This is the first patch that went into the kernel. John over there made that in 2014. So that's been over 4 years ago. That's when things really started rolling, how we fix it in the kernel. We introduced a 64-bit time type and started converting device drivers and anything inside of the kernel to eliminate the 32-bit types. We have found most device drivers using those types, literally hundreds of patches for device drivers. I've had good help from interns through the Outreachy program. We've used it as a startup task for getting new assignees onboarded into Linaro. So we get a lot of assignees that don't have exposure to the open source process. So we use that as something where you could easily find a driver that is known to be broken. It's obvious how to patch it, and then you have to convince the maintainer to take a patch for it, which happened to be a really good starter task. But at the rate we were doing it, we weren't actually making a lot of progress getting through the hundreds of drivers. And then the core timekeeping code, that's the one that John was most involved with, that has actually been done mostly for a couple of years. There's still some corner cases that we have to clean up after the last user of some interface is gone. And the file system code that's the one that I started working on. I think it was around 2012, and I posted patches in 2014. I handed it off to Deepa, who was an intern through Outreachy for me a couple of years ago, and then she worked on that a couple of years ago. And she finally got it into, I think, the 4.17 release, which is when Linux merged those patches. So it's really been 6 years working on this patch set. And then the system calls, that's the other really big area aside from the file systems, and we're in the process of completing that. the moment. I'll get to that later. So what do we do? So anything that uses a time t in the kernel, we try to find a better type for it. The easiest conversion would always have been to use a 64-bit time 64t. That's the one that John introduced. But we also tried, when we fixed those drivers, we tried to clean up the kernel and make it better in other ways. For instance, a lot of device drivers just use the do-get-time-of-day function to get a microseconds accuracy value representing the current time in terms of UTC, and then measuring elapsed time with that is actually a really bad idea, especially if you're trying to measure small amounts of time. First of all, you always have to convert nanoseconds, which the kernel timekeeping code uses, into microseconds, which you're using, and then you have to calculate the time val into a whole number of microseconds. And then it changes if somebody calls set time of day, or if you have the NTP protocol in use to update the rate that time is moving at. It could also jump, and then you have something called leap seconds that most of you probably heard about. Yeah, John has particular experience with that. And the best way to deal with it is just not to use clock real time, but use clock monotonic or one of the other time bases that are completely independent of the current time. It just starts counting when you boot the system, and then it keeps counting monotonically, as the name says, in nanoseconds. So a lot of drivers where we changed it away from time t or time val or time spec, we ended up using monotonic time as well, which fixed other problems in the process. Another area is the I/O controls. That's the interface between a device driver and user space. These are commands, like on the system call level, you call the I/O control system call, you pass a command number, you pass an argument as a pointer, usually. And the command number, in most cases, encodes the type of argument by taking the size of it. So you have an I/O control command that is defined by a subsystem identifier, a number for the command, and the size of the argument. And if we pass, for instance, a time spec, the argument length may be either 8 bytes on a 32-bit system or 16 bytes on a 64-bit system. And if we fix user space to use the 64-bit time t, then it will also be 16 bytes long. So one patch that we merged, I think this is one that Baulin did. So instead of handling the native command, we handle a 32-bit command and a 64-bit command in the I/O control function. So the device driver just knows about both formats, and user space. I have that on the next. No. So user space gets the command definition based on struct time val. And this is a different command number depending on the configuration of the C library, because the time val type is defined by the C library, and when we change it to 64-bit, we get a new command number. So the device driver now gets changed to handle both the old command and the new command. That means the device driver doesn't have to know which mode the user space is running at. That's a very important concept that we don't have in new binary format. The kernel treats binaries with a 64-bit time t exactly the same way as 32-bit time t, except they use slightly different interfaces, like a different command number for I/O controls. And this is the easy case. So a harder case is the socket timestamp. This is a patch that I just prepared for the current release and that I probably have to redo. I'll get to that in a bit. So here the command code is a really old command code that dates back to the time before we had those macros. So the command code is exactly the same on old user space and on new user space, independent of what the time type is. The workaround that we did here makes this even more complicated. So we redefine the macro depending on the size of struct timeval. If it's 8-byte, we use the old command code, which is then redefined to be the old number. If the size is something other than 8-byte, which has to be 16-byte, we use the new command code, which is defined to be 2 64-bit words long. And then we can do the same trick in the device driver and just handle both. And it gets more complicated than that. So if it's not an I/O control, but it's a read command, so the input subsystem, you have a file descriptor for a character device. You read an input event, like someone pressing the clicker, someone pressing a button, someone moving the mouse. That's an input event. Each input event has a timestamp on it. And this input event, I have it here, has the time val in it traditionally. So the input event structure is incompatible when you change to a new glibc with a 64-bit time t. You read a structure from the kernel, you actually get less bytes than you expect. So what we did here is we redefined the input event structure to only use time val in the existing cases. And if we have a glibc version that happens to use 64-bit time t, that's a macro we can test for, then we redefine input event to use a 64-bit, to use an explicitly sized seconds and microseconds value that is the same size that it was before, but we're not referencing time val anymore. So we're not using 64-bit time because we can't. That would be a change in the binary interface. But we're lucky because the timestamps are already in clock monotonic. And we don't need the extended range because clock monotonic, as I said, we have 136 years after boot up. And that's where we say that's enough. We don't need 64-bit for that. So this is a fairly ugly workaround. It basically means that anything using this structure needs a code source change once you get the new header file. The binary interface will remain compatible, so any old binaries work. And we know that there's only a few libraries that actually use this input event structure directly. So usually you go through libevent, and we only have to change libevent to understand the difference. And all users of libevent do not have to be changed for this. And it gets one level more complicated. This is an example of a memory mapped structure that we have in the kernel with timestamps in it. This is the one for audio timestamps. The trick is very similar to what we did for the input event, and this is not merged yet. So the idea is that instead of using timespec, we use a new sound monotonic timestamp. We also have to change all users to use monotonic timestamps instead of real-time timestamps. And then we can map this into user space again. Because otherwise, you might have multiple user space processes mapping the same page into memory and trying to interpret the bytes in that buffer in different ways. So this is the best we came up with. We still have to discuss this further with the audio maintainers because there are different ideas. Like there's possibly a different way of fixing this. This is what we currently have. This is what I said, the virtual file system layer. That's the work that Deepa did most of the interesting parts of. Dave Howells implemented the statx system call, which was very useful. We have almost a dozen different implementations of the stat system call in the kernel with slightly different behavior. We have lstat, fstat, we have old stat, new stat, stat64, and all permutations of those. And the statx system call is just a superset of the functionality, and it always uses 64-bit timestamps. So we're now changing glibc to call statx underneath, and at least on new kernels, and that can implement all the old stat variations that user space uses. And then we have to change all the file systems. We have to, like the big change that we did was in 4.18, getting the virtual file system code changed, but that meant that all the file systems still internally convert from 32-bit time T to 64-bit time T. And we have to get rid of all those conversions. This is something I did for 4.19. For almost all the file systems, there's just 3 or 4 that are left. With the system calls, we had an interesting trick. So basically, we identified around 50 system calls in the current kernel ABI that pass a time T in or out of the kernel. And for each of them, we have to have a replacement. A lot of these system calls already have a replacement. So for example, I mentioned the old stat system call, and we already replaced it twice with new stat and stat64. So stat64 is the one that's used. And unlike the name suggests, it still uses 32-bit timestamps. And now we have statx. That means we can just ignore all the old stat versions. But for the ones that we do need to keep, we now need to have 2 versions of them. So for example, for clock get time, which is what you use to read the current time, we need to keep clock get time. We also need to have clock get time 64 to get it in a different format. And that means adding a lot of new entry points. What we did instead is that we noticed that we already have 2 implementations of each of those. There's one that is used as the native system call in each architecture, and one that is used for compatibility with 32-bit user space running on 64-bit architectures. So we are reusing the compat system calls so that we don't have to add a 3rd version of each of those system calls. So originally, this is one of the system calls in this set. On a 32-bit system, you have a function called sysfutex, which implements the futex system call. On a 64-bit system, you have a system call by the same name with a slightly different set of arguments because it uses a 64-bit time T. And then we added the compat version of that, which you see has the same calling conventions as the native system call on a 32-bit system. Now we're adding the same compat system call to 32-bit systems. And this is what we've been doing in 4.18. So about half the system calls that need this, now we have a compat system call that you can enable on 32-bit systems. And then something happened. Christoph Helwig reviewed the patches and said, well, this is not a good idea, because this is really confusing. Why do you have a compat system call on 32-bit when you don't have a compat layer? You don't have a completely different set of binaries. You just have another system call. And that's where we renamed everything. So instead of having a compat timespec in the compat futex system call, we now have an old timespec 32 argument. So I did a patch to change all of those data types to get rid of the compat name. And then we are going to rename the system calls, the entry points, so that the function name is sysvutex time 32. And that will be the same name on 32 and 64-bit system calls, systems. And once that is done, we can change the system call tables. So the regular sysvutex entry point refers to the 64-bit format, and the sysvutex time 32 refers to the 32-bit arguments. And we do the exact same thing on 32 and 64-bit kernels, and I think that's a very nice way of handling this. Right. Then there are the data types in user space. So as I said, we have timespec and timeval are typical structures. We introduced a new type, kernel timespec. We just tend to use the kernel prefix in type identifiers in kernel headers, so we don't conflict with the glibc types anymore. Like, this is actually causing us a lot of problems that we have a timespec type defined in the kernel, which is now different from in the exported user API headers that is different from the timespec definition in the glibc header. So we're trying to get rid of the private types, and there will be there is a kernel timespec type in the kernel headers, which uses 64-bit seconds and 64-bit nanoseconds, and that's what we use at the interface layer. And this was something that Linus really strongly argued for, that we have a 64-bit nanoseconds as well as 64-bit seconds. Because when you're copying a data structure from kernel space to user space, you typically use a copy to user function, which copies the entire 16 bytes of that structure. If we had made the nanoseconds long, or explicitly 32-bit, which is totally enough to count the number of nanoseconds within a second, we would have padding in there, and copying that to user space means we're leaking data that is on the kernel stack that might be turned into an exploit from malicious user space by reading data that it should not have access to from the kernel, such as the location of functions inside of the kernel. If you can find the location inside of RAM that the kernel resides at, that allows you to do a number of other exploits later. So using a data structure without padding helps avoid those exploits. It also helps that we can share the implementation between the native 64-bit system call and the 32-bit user space running on a 64-bit kernel, which now has the exact same layout. These are all the system calls that we identified that already have a replacement that still uses 32-bit time T, and we added replacements for most of these in 4.18 or earlier. So there are, as of 4.18, there are only 5 system calls left that don't have replacement with 64-bit time T yet. And in 4.19, Thomas Gleixner just yesterday merged my patches for an additional 3 of them. So that leaves us with adjust timex and wait for. This is a similar set of system calls. These are all the ones that we absolutely have to provide to user space because there's no other way of calling those. And for each of those, we have to have a direct replacement with a 64-bit argument. And again, about half of them we have fixed in 4.18. And another set of system calls is already merged, or we have the patches. I'm in the process of integrating the patches from dpuf for the second half of the red ones. Then we are left with a small set of system calls. And the only one that we absolutely have to do is actually the clock adjust time. All the other ones we might be able to implement on top of the 32-bit argument because we're only passing relative times, not absolute times. So that would be a little bit ugly, but it's totally doable. One example where we have to come up with either conversion in user space or change the kernel is the get R usage. This uses the R usage data structure that's the same as in the wait for system call. This starts with 2 time val members, and this is actually the same structure layout across all the operating systems that I've looked at that implement these system calls. So if you look at any Unix, BSD, even Windows, I think, has an implementation of these system calls in some libraries, and they all use the exact same structure layout. And that means that we probably have user space code that has a copy of this data structure in their source file. So even if you change the kernel headers, we might get user space expecting the wrong data. What we do here is, again, similar to what we did with the I/O controls. We have a get R usage time 32 system call. And we change the header so that if you are building an application that uses the old types, that if you're building an application with 64-bit time T, you get the kernel old time val type instead of the time val type, which is then 32-bit. If you call the system call directly, and glibc can call this and convert it into this structure, which has a different layout. And the other way to do it is to have the 64-bit version of that, which is, instead of using a time val, we would use a kernel time spec. That means we also get nanosecond resolution, because all the interfaces that we introduce as replacements have nanosecond resolution. I thought this would be nicer. So that's the current plan. And then we have to implement this on 32 and 64-bit architectures, still using the same structure. And then user space sometimes has to convert between nanoseconds and microseconds, probably in glibc. This is the time spec that I looked at earlier. This is actually the definition as it would be used in glibc. I didn't exactly copy it, but this is roughly what it looks like. I said that we, in the kernel, want to have a 64-bit nanoseconds value. In user space, we don't. In user space, we follow the C standard, which says the tvnsec member of a time spec is of type long. It's in POSIX, it's in C99. None of the C library maintainers want to diverge from the standards because they implement the standards, the whole point of a C library. So we have to match the layout that the kernel provides and implement padding. So if you're on a little endian architecture, we have 32-bit tvnsec, and on 32-bit we have 32-bit padding. If we're on big endian, we also have padding, but instead of giving it a name, we use an anonymous bit field. The reason for that is that there's a lot of code that puts a time spec structure on the stack and initializes it by assigning something to the first member and something to the second member. If we had the named padding field as the second member, that would initialize the padding to the desired value and leave the nanoseconds as uninitialized. We don't want that. So this is probably what it will look like, or something slightly more complicated than that. Right, should have. Then we also have the time val, and this is something that I only learned about last week, unfortunately. I always thought time val was easy because we define in the standards it's not using a long microseconds value. It's using a SU seconds T type microseconds. And this is defined by the kernel. And I always assumed it would be defined in a sensible way, but it's not. There's one architecture, which is Spark 64, that defines it as 32-bit for compatibility with even older operating systems. I assume Sun OS, possibly something else. And that's why we now have, in case of Spark, we have in 32-bit microseconds, followed by padding. And for everything else, we have 64-bit microseconds. And then we have to have the 32 and 64-bit version of that. What it means for the kernel, I had nicely implemented some functions that can write to either timeval or timespec and either 32 or 64-bit versions of it, and run it either on 32-bit or 64-bit architectures, and all look nice. And now we have one more case, because 64-bit Spark timeval is different from all the others. So I have to go back and rework some of my old patches. Then a little update on the C library. So we have two C libraries that have started looking into this problem. Once we change the kernel headers, like once the API between kernel and user space is defined, we can actually get this into C libraries. And glibc, of course, is the most important one. And we have a plan that is already a few years old that Albert started working on, and you can read it all at this URL. What's interesting here is the C library will allow you to build an application either with 32-bit time T or 64-bit time T, and it will run on old kernels and new kernels. So you get all the flexibility. The one thing we don't allow there is to run a binary that was written with 32-bit time T. It may not run on a kernel that only has 64-bit time T, because we explicitly disable compatibility support. The idea of that is, if you want to prove that your system works beyond 2038, you may want to disable all of the compatibility code that we put in for existing binaries, because every time you have a compatibility interface, this is something that could break. If we remove them, it breaks now instead of later, and that's better. But most people will have it enabled, so everybody will still be able to run their 32-bit binaries until 2038. In Muzzle, it's completely different. There's no compile time configuration of Muzzle. It's always the same ABI, and the ABI at the moment uses the same time T that we've always had. So we will have to have a new incompatible version of Muzzle. And I'm calling this 2.x. Could be named something else, but there will eventually be a version of Muzzle that has a 64-bit time T. There's still an open question about whether that will or will not run on old kernels. If you want to run it on old kernels, there's a problem with device drivers and I/O controls and the memory mapped interface and all of that. But there are also some reasons for doing it, so we'll see. The port that I did has an ifdef, so at compile time for the C library, you pick whether you use 32-bit or 64-bit time T. The version that will go into the official Muzzle will probably completely get rid of the 32-bit time T. That's at least my understanding. And then further down the road, once we have the kernel and we have the C library, we can finally start with the distributions. Because if you don't have the whole distribution, all of this is meaningless. If you have one application that stops working on the system that you want to run in 2038, you lose if it doesn't work. So you have to rebuild everything that uses time in any form. rebuild it against a new C library with 64-bit time enabled. For the embedded distros, that's very easy because they always rebuild everything from scratch. So once we have patched Open Embedded, then any Open Embedded user that enables this will get the whole user space using 64-bit time T. For Android, it will be very interesting. I have no idea what we're going to do because we have fixed API levels, and you can write applications against a certain level, and it will run on all later levels. But now we would basically have completely incompatible API. So instead of ARM32 level, I don't know, 22, you would have ARM32 with 64-bit time T level 22, which is incompatible with the old one. I have no idea. I don't think anybody has really thought this through for Android yet. It is going to be a big problem if there are Android devices that want to run that long, which I assume there will be, but so far we haven't discussed it. And then for 64-bit distros, we still have to deal with all the hardware interfaces and file systems and file formats, but we do not have to deal with rebuilding user space, which is a big relief. And then 32-bit desktop distros. These are the main ones that I could find that still support 32-bit user space in any kind of form. And out of these, well, we have to either stop using them within the next 19 years, or we have to rebuild them completely. Most of them will probably just stop being used at all. The ones that are the most likely to still be relevant in some form or another, usually on an embedded system that happens to use a desktop distro because it's what the embedded developers chose. That will be ARM 32-bit or x86 32-bit. All the other ones, I assume, will not make it. So anybody who, there are lots of people who have shipped these in the past, but most of the developers have moved on to ARM or x86 or 64-bit systems. This is the overall progress where I think we are at this moment. These are the different areas that we talked about. For device drivers, we are pretty much done. There are still some drivers that need work. The core timer handling is almost completely done. We just have to, but once we remove the last users of some old interfaces, we can remove the compatibility code inside of the kernel that we still have. System calls are progressing nicely as of 4.19. The driver interfaces into user space, we still have a couple of them that we absolutely have to fix, and we don't have the final patch yet that includes audio, video for Linux, sockets, and a few more. File systems, the big work has been done. There are still a couple of file systems that we want to fix, and there are some corner cases in some of the file systems, like what happens if you set the time to a value that is not supported by the file system. Currently, we just wrap around. You could basically end up with a random time that depends on the underlying file system because anything could happen after the wraparound. We need to change that so that if you set the time on the file system to a future date or a date in the distant past, that it just truncates to the extreme values that we still support. So if on an ext3 file system you set the timestamp on an inode to 2040, the result should be having the timestamp on 2038, or you should get an error. But the current behavior of setting it to somewhere in 1904 is just not acceptable. Then architecture specific, that's mostly the system call tables. This is something that my colleague Firos has worked on. We are going to change the layout of all the system call tables. Currently, all of the older architectures, like the 10 earliest architectures that we still support in the kernel, each of them formats the system call table in a completely different way. Changing those tables in a controlled manner is very hard because you have to understand every single architecture at first. So what Firos has been doing is trying to get a common format of how we describe the system call table in the kernel, and then we can do the changes on top. So those patches are not upstream yet, but he's done a lot of work on it. And then we have the C library and the distributions. And this is all that I had, and I hope you have some questions.
Yes. Has anybody thought of updating POSIX or single Unix spec for this kind of work? Because obviously all the world isn't quite yet Linux.
So, in what way updating it?
Well, for example, to deal with the new interfaces and, you know, the things that are exposed by the C library, for example.
I don't think there's a need for that. I haven't found anything that won't be compatible. Okay. So the time spec was certainly something that came up in the past for the x32 ABI, and we have solved this now by having a different definition of time spec in the kernel user space interface compared to the C library to application interface, so that we can get all the constraints right. But with that, I don't think we need to change to POSIX. If something like CPIO is specified in POSIX, then we may have to change that.
Sure,
but
yeah,
I'm not aware
I think
of
there's quite a few things like that where POSIX does have some relevance. So, you know, I'd expect there's going to be some changes needed. Has anybody started talking about that yet?
I'm not aware of anything. The other thing to consider is that most of the other Unix implementations have already solved this. So macOS, BSD, well, they're the only ones that are still available for 32-bit. All the commercial Unix are 64-bit only, if they still exist. So basically, most others are ahead of us, which is something they can do because they tend to have releases where they update the kernel and the C library at the same time and all of user space. So they just rebuild the world and then ship it as a product. And that's something that we do not do. So we change the kernel and we expect all past user space to work with the current kernel, and glibc expects to work with a certain number of kernels in the past and every kernel in the future, and also work with all applications built against an older glibc. So we have a whole lot of issues that we get from the compatibility guarantees that we make. But the POSIX should already describe what the other Unix architectures, the other Unix implementations do, and that I think works fine. Yeah.
So the system call interface, which like read and I/O control. So you redefine that, what that means from user space side, depending on how time spec is defined, right?
Well, let me get back to this slide here. So on I/O control, we can do it. Where are we?
So my question is, how do you do that on kernel side?
So the kernel, like this is the one that we had for the I/O control. So since user space identifies the interface,
No, I meant the ones
number.
with the structs in the, and not the one, maybe 2 or 3 slides forward.
So this was the easier one.
Yeah,
So
that one is clear.
Yeah. So we pass a command number, and user space, by compiling with a certain type, it automatically gets the right command number, and the kernel just implements both commands. So the kernel, you can always pass the wrong command, and you get the matching result for that. So the kernel doesn't know what user space is running.
Yeah, that's clear. Yeah, but when there is this struct in the read,
yes, for
slide.
read we basically lose. There's no good way of solving the read. So what we did here is to redefine the structure.
Yeah, like this one.
So that we do not use timeval in the header file. So if we rebuild the user space using a 64-bit time T, we still get the old layout for the structure. And user space has to change to not expect the timeval. If you try to access this as a timeval, you get a compilation error, and then you know that you have to change your source code. And we hope that this is only in 2 or 3 libraries that actually use this interface. But this is one of the harder things. And we don't have a good solution for this other than changing the user space source code. But this is also true for a lot of other things. So any user space application that assumes that 32-bit is enough to store a timestamp will have to change as well.
Yeah, and that's
So
at some certain future point
Yes.
in time
So
where we can do that.
we certainly have to change a number of applications, and any application using an interface like this may be affected by that too.
So, of course, that's why we need the 64-bit interfaces available as soon as possible so people can start converting.
Yeah, absolutely. Yep.
Once we get, excuse me, once we get the kernel squared away, we're going to discover problems idiomatic to languages or to development platforms or whatnot.
Yep.
One that I'm aware of is a fairly old time interface in 32-bit PHP code where there's a function call that will fail on 32-bit systems when the time wraps around. Do you have a sense for if someone were to want to put together a test suite for auditing code or for looking at code, where you would even start now, or is it too early to even start that audit process?
You can't really start before we have the C library. Like if the same problem exists on 64-bit systems, you can start now. It depends on what exact set of applications you want to test. I don't know what tests you would do, but anything that uses the same code on 32 and 64-bit architectures, you can already test on 64-bit architectures by setting the time ahead and see what happens. For testing on 32-bit architectures, I only have this one prototype of Muzzle that we have tested. It passes the LTP test suite, and any application that you could link against Muzzle, you could test with this in theory. But it's also, like, this will still change. This has an earlier version of the system call interface. We've made some changes to the binary structures that we're adding. So this is all still very early. It would be much easier as soon as we have the system calls in place and we have a C library that is close to what we will eventually get. Related to that, you mentioned PHP. The one that we've come across a while ago is Python. So Python has a binding for C libraries. And the way this is written is that it assumes that the time structures are always using long. So it is already broken on the x32 target, on x86, which fortunately nobody uses. But they will run into big problems, and I'm probably not going to work on those, but whoever is going to work on converting Python will have to come up with a clever way of dealing with this in general, because we're changing one of the fundamental assumptions that's in all the native interfaces that Python uses to talk to libraries and to the kernel. And I assume there will be more of those.
Of course, probably the biggest amount of work is going to be nearer the end of the process. There's going to be any number of on-disk formats which are going to be embedding time and date stamps that we don't know about yet.
Exactly.
And you talked about file systems. Obviously, the VFS layer you've changed. I was curious about things, like some of the standardized file systems like ISO 9660. Is that clean for 64-bit?
So ISO 9660, this one is 2038 clean. I believe it uses an 8-bit number to encode a year starting in 1980. So it will overflow in 2236.
Cool.
Yep. And I have a list of all the file systems with an estimated expiration date.
Yeah. In fact, do you have that kind of information available readily online? I know in the past you've given a link to that.
So say that again.
Do you have, say, a link to any documents about what you have, say, the list of the file systems and what
yes, I
works you
should have.
think?
I think those slides will be available. I'll put the links into the slides in the version that will be available for download.
Awesome. Because I actually had a friend contact me last week. He works for a supplier to a car manufacturer, and they're already starting to ask the question, so why can't we set the date past 2037 on the infotainment yet? So it's good to see that people are starting to care about this, good and early, but obviously there's still a lot of work to be done.
Yep. No, most of the documents we've written years ago, so that might be slightly outdated information, but those links are still very helpful, I think, so I'll put them in here. And we're out of time. So thank you very much for attending.